Good afternoon and welcome to Likeable Science. I'm your host, Ethan Allen. We're broadcasting here from the ThinkTech studios in downtown Pioneer Plaza. Likeable Science is all about how science is fun, dynamic, accessible to everyone. Everyone should enjoy science, and I have a guest today who is going to really, I think, blow people away with his new scientific development. My guest is Elliot Hawkes from Standford University. He's joining me by Skype. Elliot, welcome.
Hi, thanks for having me, Ethan.
Hey, good to finally meet you here. So Elliot is a Ph.D. candidate in mechanical engineering at Standford University. He got his master's there a few years ago, about 3 years ago, and his bachelor's also in mechanical engineering back from Harvard University a few years before that. We're going to talk today about Gecko-inspired adhesive, and in particular how Elliot has, to use a pun, scaled that up to a really interesting level now. So maybe just to start things off, Elliot, tell us a little bit, if you would, about sort of what's the basics of the whole gecko, how geckos climb walls and run across ceilings and all.
Yeah, so an interesting thing with the gecko is that it uses van der Waals forces.
What are van der Waals forces?
Yeah, so van der Waals force is a force that's between any two molecules. You get them close enough, they momentarily attract one another. So you can imagine if you get two surfaces very, very close together, they'll actually get points in contact, and those points will attract each other. Now, on most things, like if I take my hand and touch my other hand, I don't feel the van der Waals forces because there's only really a few points that are close enough to touch. But on a gecko, it has millions of tiny little hairs that are very long and soft. So that when it brings those hairs in contact with the surface, millions of contact points arise, and then you can multiply that tiny van der Waals force by millions, and you actually get a pretty large force.
And does it, just so I have the picture, when the hairs are sort of standing up straight, there's a relatively small surface area, but as soon as a little bit of pressure is applied, then they're sort of bent over, and the long axis of the hair, as it were, is now in contact with the surface, and that makes for a much greater surface area. Right?
Yeah, so you can imagine, this could be a hair where touching the surface, and when it's just like this, it doesn't actually stick. But then when it pulls down on the wall, you get this whole length in contact.
Right.
And that allows you huge area, which then area times the van der Waals force gives you a huge force. And so when it releases its force, it's just a little contact area and can come off very easily.
Okay. Nice demonstration there. I like the giant hair. But that's really good. It really helps people understand what this is. So obviously geckos have been doing this for a long time. But a few years ago, scientists got curious about how geckos did this, right, and sort of looked at their feet very closely and began to discover this. And I recall even, I think maybe 4 or 5 years ago, people began making so-called gecko tape, right?
Yeah, exactly. So I think it started in 2000, 2002, around that time. Keller Autumn, a biologist at Lewis and Clark University, discovered that this is, what we're talking about here, this van der Waals force was how the gecko actually sticks, because people weren't sure, it could have been suction, or it could have been capillary, something to do with excreting a liquid, and having that help stick. They just wanted to figure out if it was actually this van der Waals force, and so since then, people have been trying to make gecko-inspired adhesives, and the one, we made one in our lab, which is definitely not the only one. I think we've counted recently, and there's 384 publications on gecko-inspired adhesives right now. So there are a lot of versions out there.
Yeah, excellent. And the issue, I guess, at least one of the issues is these work pretty well in sort of small bits, small areas.
Yep.
And fairly effectively, but there's been an issue that you can't start using, you can't make big sheets of it, and
yep.
It doesn't work well.
Yeah, so it's interesting, and if you do look at those 384 papers, the vast majority of them are, testing very small samples. So they make, something maybe a few millimeters by a few millimeters, and they test it on a piece of glass, and they pull it off. they get very good adhesion. There's even people who are getting adhesion higher than the gecko can get on these very small areas. But it's interesting is once you try to scale these things up to a larger size, you keep adding more and more area, but the force is only barely going up. Because it turns out it's difficult to get all of your tiny little fibers to touch over this huge area. And then once you get them all to touch, it's very important that they all have the same force in them. Because if only a few of them have the majority of the force, then you're not going to have a very large force.
Right, and this is one reason why the gecko toes are sort of frilly looking in a sense, right? They're spreading this stuff out in a lot of small strands, as it were, strands of strands.
Yeah. It is interesting, even with the gecko, so, you know, we've been looking at the gecko for inspiration for all these years, and it turns out that we started taking some, or other people have started taking some measurements on how the gecko's adhesive performs when you measure a tiny, you know, nanoscale area of it versus, you know, you scale up 100 times and you measure another slightly bigger area, maybe even a whole toe, then a whole foot. In the adhesive ability decreases with each of those measurements. So on the very small scale, it's amazing, way, you know, 1,000 times better than our adhesive. But as you keep going up and up, by the time you get to his hand scale, it's not even any better than ours.
And so this makes sense in that we don't see 100-pound geckos running around, right? We don't even see 1-pound geckos running around. Geckos typically are pretty small lizards, right?
Exactly. The biggest lizards, biggest geckos that are extant, so in existence, are around 300 grams, something like that, so less than a pound. And then the biggest thing that we know to have ever climbed is around a kilogram, so that's about 2 pounds, a little over 2 pounds. Exactly, nothing in nature. And then you look at bugs, you know, there are millions of bugs that are climbing with adhesion. So the smaller you go, the more and more things you get. So it's kind of, it hints at that the bigger you get, the harder it is to climb.
Right. You run into it's a whole scaling issue there. The classic illustration being that you can drop an ant off the Empire State Building and it survives that fall just fine, but you drop an elephant from 4 feet and it kills it, right?
Yeah. Yeah, and there's an interesting thing called the square cube law, which just is related to that, where basically as you get bigger, your surface area gets larger. So imagine if you have like a Rubik's Cube, or, you know, just a cube, and you have a small one, and you have a much larger one. The surface area of the large one goes up as the length squared. However, the volume goes up as that length cubed.
Right.
So we started with, you know, I don't know if it's worth going through the math on that, but basically the cube gets larger much faster.
Right.
So when you're a gecko or a human trying to climb, your adhesion, the force keeping you on the wall, comes from the area.
Right.
The thing that's pulling you down to the ground, making you fall, is your mass, which is correlated with your volume.
Exactly.
So as you get bigger, your volume's going up much faster than your area is, and it becomes harder and harder to climb.
Right. So let's show a picture just to give our viewers some sense here about what we're talking about here. Okay, so this is you up on a essentially glass wall, and no harness, and literally the things on your feet are not.
They're not helping either. Yeah.
Right. All you're really hanging from is these 2 pads at your hands, right?
Yeah. Each one has about 140 square centimeters of adhesive, which is about the area of one adult human hand.
Mm-hmm. Wow. So that's very impressive that can hold you up that well. And we have another view that maybe gives a little bit clearer view. It's sort of a triptych view, I think, of you. It shows you. Oops. Okay. That's a different picture. Okay. That's, I guess, you just placing one of those on the glass in front of you.
A little closer view of the device.
Yeah. Yeah, this is what I was talking about. So this is sort of a time-lapse series, as it were, of you starting out low on the left and going up higher on the right now, just by moving your hands. So let me just ask you a few basics about the sort of the mechanics of this. I mean, it strikes me it must be difficult in a sense. You're hanging by your hands and arms alone, and you're having then to pull yourself up.
Yeah, so that was actually an interesting discovery we made, was that you don't have to climb. So it looks like I'm doing that, but it turns out all my weight's actually in my feet. So how the device works is I place the adhesive pad with my hand, and then there's a cable that runs down to my foot, which allows me to stand with all my weight on my legs. And we designed it like this because humans, unlike geckos, don't have very strong upper bodies. We're evolved to walk and run and move around our legs. There are a few very special rock climbing humans who can probably pull themselves up the wall with just their hands, but I can't. I'm a bicycle rider, not a climber. So my strength's definitely my legs. And so that was actually one of the big considerations with the design, is how to transfer the load to my feet. And so, yeah, when my right hand adhesive pad is on the wall, all my weight's in my right foot, and then I'll pick up and place my left adhesive pad higher, and then I'll step up and shift my weight over to my left foot, and then on the right, and shift to the right, and just keep going like that.
Ah, so you're not really pulling yourself up by your arms in any sense. All you're doing is sort of just making more or less effortless steps up.
Exactly. Huh. And we can see, we'll see a video a little later. Actually, at the end of the video, I take my hands completely off because I'm not allowed to need them.
Huh. Okay. Interesting. So, so that then you actually gets past sort of my next question. I was going to ask you how you dealt with obstructions in the wall, but if you are pulling your hand completely off, of course, then you just go around the obstruction, go over it, and get to the next sort of flat spot.
Yeah, exactly.
Excellent. And just out of curiosity, I'm still a little puzzled on that basic design. Why didn't you sort of incorporate knee pads and maybe toe pads that you would, elbow pads, you'd have multiple?
Sure. So it's an interesting problem with the Gecko adhesive. It comes back to what we were talking about before, about the adhesive works best when you've actually pulled down on it so that it lays along the surface. And our adhesive works like that too. And so I want, when I'm climbing, the load from the pad to be at an angle. So this is the glass wall. I want the load, maybe you can't see that. I want the load to be as shallow as possible. So very close to pulling straight on the wall. So if I pull straight out, it comes off, right? So I actually want the load to be close to straight down. So it actually works best to have a pad up high and then a string going down to my foot, because it actually keeps the load very close to the wall. And we measured it, and it's only about 7 or 8 degrees. The angle from my hand pad going to my foot, where the load's going. Huh. So if I had done separate feet pads, and it would have ended up, it's a little more complicated, but if you can imagine, this is me on the wall, and if these are my feet and they're stuck, I would tip over backwards, and so the force up here would actually be straight away from the wall.
I see. Okay, right. You don't want to do that at all, because
Going away from the wall. So it's interesting. It's kind of a subtle point. It's not obvious, but it turns out it actually works better without adhesive on my feet. So those things on my feet are actually allowed just to slide up and down the wall.
Huh. It's very, very sort of counterintuitive, but
yeah, exactly, absolutely.
Very, very neat. And now you developed this technology in combination with some folks from DARPA. Do I understand?
That's correct. So we started that project a while back. That was maybe 5-6 years ago, and it was called the Z-Man project. And the goal was exactly this: to get a human to climb up glass. However, our part of that project was not working on the human climbing aspect. it was on developing adhesive. And so it was through that project that we developed our adhesive, and you gave that technology to DARPA. And then that project ended a couple years ago, and we have a new project, which maybe we talk about a little bit later. It's with NASA, grasping space junk, so it's kind of a fun one. Anyway, so that was more where we progressed, and we're working on scaling this adhesive up to large areas for grabbing these satellites, and then it was just too much fun not to try climbing these big areas of adhesives, and that's where it came.
I can see, yeah, from that, it looks like that must be a very intriguing
Yes.
activity to do.
Yeah.
So anyhow, I think we're about ready to take our first break here. I'm Ethan Allen. I'm your host on Likeable Science. I'm talking with Elliot Hawkes of Standford University. We're talking about scaling up Gecko-inspired adhesives. We'll be right back.
Hi, I'm Jay Fidel. I'm host of Hawaii, the State of Clean Energy. Indeed, we want to make Hawaii the state of clean energy. We talk every Wednesday from 4 to 5 p.m. with people from the Hawaii Energy Policy Forum and guests from every corner of the energy community. We want to make energy the most important thing. It is the most important thing in the state, and we want to make everyone aware of what's going on in clean energy in Hawaii. Come and see us, 4 to 5 p.m. on Wednesday. I'm Jay Fidel. Thanks. I'll see you there.
Aloha, my name is David Day, and I'm really interested in international business, foreign policy, geopolitics, and national security, and that's why I host ThinkTech Global. I bring in guests from all over the world who know about these various issues in enormous depth and detail. Come learn with me every Thursday afternoon right here at 4 o'clock. I'll see you there.
And we're back here on Likeable Science. I'm your host, Ethan Allen. With me today, joining me via Skype on ThinkTech Hawaii, is Elliot Hawkes. Elliot is a PhD candidate in mechanical engineering at Standford University and has overcome one of the real technical challenges in this whole burgeoning field of Gecko-inspired adhesives. And Elliot was telling us before our last segment that they're getting on towards 400 different peer-reviewed publications on Gecko-inspired adhesives now. Many, many different types and varieties. But the issue has always been one of sort of the scale, that this stuff works fine in tiny, tiny areas, but as you make it in larger areas, it's not nearly as effective. And he has designed a system that really helps overcome a lot of this. So one of the tricky things, Elliot, as I understand it, or one of the key aspects, I guess I should say, is in these pads that have 140, you said, substructures, 140 small sort of postage stamp size patches. You have some set of I think you call them degressive springs and tendons that help distribute load. Could you explain a little bit about that, please?
Yeah, absolutely. So the concept. So like you said, there's a set of postage stamp sized pads, so about an inch by an inch, and we have 24 of those, 140 square centimeters or 24 square inches of adhesive. So what happens is you can imagine you have 24 of these little tiles, and once you place it on the glass, each one of those has a tendon that comes off of it, and that's where my load goes through. But you can imagine some of those tendons might be tauter than other ones, so some might be slack to start and some might be tight. And what would happen if there were no springs is I would stand on it, and maybe let's say 5 of them are tight to start. Those 5 would all have tight tendons, and you pull down on it, and all my weight would go into those 5 tiles. And since each tile can only hold about 10 pounds, I would rip those 5 off and I would fall. So that's not good. Right. So instead, we have these things we call degressive springs, and attached to the base of each of the tendons is one of these degressive springs. And so you can imagine, so a degressive spring is a spring that gets softer the more you stretch it. So most springs, like this one I got here, is just a metal spring. I stretch it a little bit, and it gets stiffer, and then it gets stiffer and stiffer, and then you can feel this too with like a rubber band. Right. You take a rubber band and stretch it, at first it'll be, pretty soft. When you get to the end, it almost won't stretch at all anymore. And it kind of, it's this feeling where it bottoms out.
Right.
And so that's not very good, because what will happen there is if we go back to a previous example, we had the 5 that were initially tight, and then we would load it, and these 5 would start stretching with our regular rubber bands, and then the other, maybe 5 or 10 would start getting some load. But these ones eventually would just hit that point where they would all get bottomed out, and then all 5 of those would rip off.
Right.
And then we were back where we were before.
Right.
So,
bipolar.
So what we did is we added a spring that actually gets softer as it gets stretched. So it feels a little bit maybe like chewing gum. You can imagine if you pull a piece of chewing gum and just keep stretching like this. What's interesting about that is it means that it could be stretched this much or this much, and it'll have the same force. And that's the key. So
Right.
that means that, so these first 5 are tight, they stretch, but they get to this kind of plateau where as they keep stretching, it's the same force. So they'll stretch, and then these other ones start stretching, and now even though these have stretched a lot more than these ones, they have the same force. So now all of a sudden, all 10 of these have the exact same force. And you can keep going until you get all 24 with it all having the same force. And that means that you get an even load on all your 24 tiles, and you can support the maximum possible load.
I see. So that basically, if more load comes on one, its tendon or its spring stretches further, and until the other ones basically step in and pick up.
Absolutely. Yep.
Cool.
Yep.
I understand we actually now do have the video of you climbing the wall up and ready to go. So let's just jump right over and take a look at that, and maybe you can talk about it as it appears.
Yeah.
Okay. So here you are. You're starting up the wall.
Yeah. And so this is a little wall we built behind our lab, and it's about 12 feet tall, and glass, and and I described the steps a little bit previously where I'll shift my weight onto the one pad, and while the weight shifted onto that side, I can lift off the other pad and shift it together, move it off the wall, and place it, shift the weight back onto it.
Oh, yes, I see now. All right, you're not pulling yourself up really by your arms at all. You're merely pulling each hand off, placing it up higher, and then just stepping up, as it were.
So stepping up, it almost feels like a movable ladder or something, where I'm just placing a rung of my ladder as I go up the wall.
Right, you've got yes, essentially a single rung ladder, as it were, that keeps moving with you.
Yeah. And the other thing to note is that each of those devices has to hold my whole weight.
Right.
Because there's points where I've lifted one completely off the glass.
Right.
It's not helping at all. So
really your whole weight is being supported by a single hand, then, a single hand's worth, or this, what did you say, 24 square inches of
exactly.
stuff. Wow. That's very impressive performance, though, from a material. And this stuff, it will work under a lot of conditions as long as it's on a reasonably smooth surface, right?
Yeah, so it stays well to glass, to polished wood, polished stone, metal, painted metal. What it doesn't work on is rough, or basically surfaces that don't have any kind of sheen to them. It does need that kind of little bit of gloss to it. And then when you see that gloss, it just means that it has a fairly smooth surface, which lets our adhesive make good contact with the surface.
Right, so you couldn't use it on tree bark or anything like that.
What's interesting is we actually another technology in our lab, we call them microspines, which actually was developed before this adhesive. It's based on the tiny little spine hooks that insects often use to climb rough surfaces. So the foot of a cockroach, it has an adhesive pad like ours, adhere, but it has these little hooks at the end that will be used on rough surfaces. And so this technology lets us stick to things that are like tree bark or concrete, stucco, bricks, a lot of external building things like that.
So you could combine the two technologies in theory and have a very versatile climbing device.
Yeah, exactly.
Cool, excellent. And so what is this material? I mean, what we've talked about these little little hairs, ridges. But what's it made out of?
Yeah, so I actually have a little piece here. So this version is, so it's made out of PDMS, it's called, it's a rubber. Here's actually two of the tiles, so these are, maybe it's easier like that, yeah. Those are two of our adhesive tiles, and this is the front of the tile. I don't know if it's easy to see, but it's not sticky at all. To the touch, it just feels like maybe like the bottom of a shoe or something. It's a similar rubber to that. So there's nothing that special with the rubber. It's a very cheap, easily cast rubber. So we're able to start with two parts, two liquid parts, pour them into a mold with a shape, and then peel it out. And that's how we get our adhesive. And this maybe can show a little bit what our adhesive looks like. So our adhesive, unlike the geckos, so the gecko has these little hairs. Ours are these kind of triangular shapes. So we call them micro wedges. But they have the same function as the gecko, kind of like we were talking before, where you touch it to the surface, it's just the tips touching. But then when you see, when you pull down, then you get these front faces of the adhesive. So when it's off like that, maybe it's easier on the red here.
Yeah, I see. Right. So you can see the.
When you pull down, you get the adhesive engaged.
Right, and this is why you say you want the forces to be essentially virtually parallel to the surface rather than perpendicular in any sense. That's because that pulls them down.
Pulls them down and makes you stay.
So all these wedges are facing the same way, and they work much better if they're facing one way than the other way.
Yeah, exactly. And then when, it's actually, they do kind of work upside down. You can kind of imagine them working. They kind of still work. I mean, we see that, but not as well. So we do face in the right direction. We make these on a CNC mill, so that's a computer-controlled mill with a very sharp blade that pokes these holes, these wedge shapes, into wax. So once we poke the these troughs basically into wax, then we pour the rubber into that, and then let that cure, and then we can peel it out, and we have a shape that looks like that.
So I think we have also a sort of a micro photograph or a photomicrograph of the adhesive. Yes, okay, so here we're seeing these same, another view of these same wedges. So each of those wedges is about how long? What's the?
So about 100 microns tall. So it's roughly human hair scale. I think the human hair is maybe 200 microns. Is that right?
Right. Okay. So those troughs are half the diameter of a human hair. So it's quite small.
Quite small, and maybe 20, 30 microns spacing.
Right. Yeah. And you can see how those would all lean over the same way. And so you said you make this out of essentially a relatively inexpensive rubber material. You could presumably make it out of a number of different kinds of materials. That's sort of the intriguing thing. The adhesive itself, again, it's a property of its shape, not of its composition, basically.
Absolutely. Yeah, exactly. And so ours is this PMS rubber, which is a fairly nice one to use. A lot of people use urethanes, which are a little tackier, so you can get a little better adhesive ability, but they also get dirty quicker, not much quicker, so that's a trade-off there. Ours is kind of middle of the road in terms of moderately sticky, but doesn't get dirty too quickly. There's also ones that are being made out of plastics, and so those ones, are harder to stick, but they don't get very dirty at all. So they have that advantage.
Huh. That's interesting. We've got a number of different versions here. And I think we have one more photograph that shows what we've been talking about here, these wedges, yes, both in sort of the upright form, as shown both on the right and up at the top, and then in this bent form, down at the bottom on the left there. And you can see that tremendous difference in how much contact there's going to be with the surface, just the little points versus the whole, well, not the whole, but a good chunk of the length of that wedge. And that's where these van der Waals forces then are making the contact, because we're talking at a scale small enough now where that level of interaction becomes important.
Yeah. And that's great for the climbing because it basically means once I take my weight, so let's say I was hanging on my right side, once I take my weight off this one, put my weight on this one, all of the wedges pop up, and now I can just gently lift that off the surface without having to rip it off or try to peel it or anything. It just almost comes off right on its own.
Very neat, very neat. We're going to go to break again here. I'm talking with Elliot Hawkes from Standford University. We're talking about Gecko adhesives and the amazing abilities that they now have due to his clever design, how to scale them up with special sets of tendons and springs to really enable him to climb glass walls. An amazing piece of research. We'll be back after this little break. I'm Ethan Allen. You're on Likeable Science.
Hi, I'm Jay Fidel. I'm here with Liz Shue, and we love agritech. In fact, she's from the Department of Agriculture, and we're underwater, gurgle, 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 and we love things that have to do with agriculture, aquaponics, hydroponics, all that. So Liz, what is your interest in this?
To grow more local food for local people.
I knew that.
Yes.
Okay, it's 4 to 5 every other Monday. Come and see us on Agritech in the Islands. I'm Jay Fidel. Come learn with us. We'll see you then.
Aloha.
And you're back here on Likeable Science. I'm your host, Ethan Allen. We're broadcasting from ThinkTech studios downtown here in Pioneer Plaza. With me today via Skype is a Standford University researcher, Ph.D. candidate, Elliot Hawkes. And Elliot has done some truly astounding work with Gecko-inspired adhesives, these adhesives that are not necessarily dependent on what the material is, but look at what the shape of the material is. These fine, in his case, fine little ridges that enable this material to hold a tremendous amount of weight if treated properly, as it were. And we saw a great video of him climbing a wall. We saw some photomicrographs of the structure of this stuff. But now I want to sort of look ahead, if we can, Elliot, and think about future applications. You mentioned one that you guys are currently looking at now is to put some version of this up in space and begin to collect space junk.
Absolutely, yeah. So it's a project we began a couple of years back with NASA JPL, and the problem is there's been, all these satellites launched up into space, and at first we thought, well, space is, there's plenty of space up there. And however, as more and more satellites go up, the dead ones, the ones that are no longer in service, are taking up valuable orbits. And so it's getting to the point now that we're running out of room in this kind of desirable orbit around the Earth. And so there's a project there that we're starting to send up a satellite that would be kind of a garbage truck satellite, you can imagine, that would go around, grab these dead satellites, and then either launch them up into the much further out orbit, where then we don't need it isn't useful for alive satellites, or actually throw it down Earth when it burns up on its way back into the atmosphere. So those are kind of two options. But the question is, well, how do you grab it? There's been different ideas, huge nets and different things. But turns out all these satellites have very large glass solar panels on them, which you can imagine is just kind of like this glass out here that we're climbing. And so, it's a perfect thing to grab with our Gecko adhesives. And so, we've done quite a few experiments down at JPL to test these adhesives, and we usually test them at low temperatures because it's very cold in space, which means glues and sticky tape, duct tape and stuff don't work because it's too cold, they freeze. But this silicone rubber does work fine there. It's vacuum in space, so that means you can't use a vacuum. It doesn't work. There's no air to suck. So you can't use vacuum, which is one of the go-to options on Earth when you want to pick up, or grab flat things. And we actually tested under radiation, because there's actually some radiation out there too. And under all those conditions, it works well. So yeah, we've been working with making sets of these And they're actually, instead of the one we use where they're just all facing the same way, we actually take two of them in opposition, and so they would pull toward one another, and that's how you get them to lay the fibers down. So they pull toward one another, and then they could grab the satellite in the structure.
Okay, I see that. So yeah, and I mean, I've gathered there are now, NASA is tracking thousands and thousands and thousands of pieces of space junk, and of course that stuff has lethal potential if it runs into a manned spacecraft, or it can certainly do billions of dollars of damage if it runs into some fancy new satellite and destroy all kinds of scientific data capabilities. So yeah, we've got to clear it out, and this technology seems sort of tailor-made for that in a way.
Yeah, and if anyone saw the movie Gravity, that was one of the problems in that movie. It caused the whole mess in the first place.
Right, but it's amazing to me that the silicon rubber still stays flexible enough in it, given how cold it is.
So it's I'm trying to remember the temperature, but something, you know, the negative 100 so degrees, and it's still flexible as well. Silicon is a very amazing material. it's very robust. And it goes to very high temperatures too. It can handle huge, 200, 300 degrees in high temperatures as well.
And again, since there isn't a lot of since you're not dealing so much with the gravitational forces out there in space, you probably wouldn't need gigantic pads of this stuff.
That's absolutely true. So what you need is just enough force to slowly accelerate the satellite off of its current orbit and then, into a different one. So we actually had a test down at JPL a couple of months ago where they have an air-bearing floor. So you can imagine it's kind of like a giant air hockey table, and they have these two 400-kilogram robots, so 900 pounds or something. Enormous things. They're floating on this air hockey table. And we put one of our grippers on the first robot, and it went around and caught the other robot, which had a solar panel on it, and then tugged it and moved it in the direction it wanted to, like that.
Cool.
So this was with a pretty small gripper. They could only pull, 50 newtons or 5 kilograms, about 10 pounds. It was like 10 pounds of force, but it was enough to pull a 900 pound robot.
Excellent. That's very critical piece here. Is that, yeah, you don't need your adhesive to be supporting 1,000 pounds or 10,000 pounds. All you need is to support enough to nudge it around a little bit.
Absolutely.
And wow, so where do you have other ideas about places, ways you might use this?
Yeah. So another one is here on Earth in manufacturing. We see it as an alternative to vacuum in moving large glass panels around factories. So it might be for automotive, for solar panels, for TV screens, anything where you have kind of a big flat sheet of glass. It's hard for, a robot can't really grab a big sheet of glass. So right now we use suction, which works, definitely works. A downside of it is it takes power, is one. And two, it leaves normally you'll see like a little ring of residue from where the suction cup was. The nice thing about the silicone adhesive is that it comes off very cleanly. You don't see any residue left. So we had a CEO of one of the big car companies here, and he was very interested in the technology because he says right now they use suction to put the windshield on, and it gives this big, ugly circle in the middle of the windshield. They can't they can't send that off to sell, so they have to do a whole other step to clean the windshield to get this smudge off it. So he saw, if you can use a gripper that comes out cleanly, it can be really beneficial.
Excellent. Wow. So that's really an intriguing range of applications if you think about from human climbing to manufacturing technologies to the removal of space junk, as it were, all based on this one fascinating idea of what the Gecko-inspired adhesive combined with your insights on using degressive springs to make sure that you get the even pressure necessary across a larger area.
Yeah.
That sort of blows my mind, quite frankly. And do you think? I mean, are you gonna stick with this and see where this particular project takes you then in the future and keep.
Yeah, we'll definitely see. So we're meeting he's actually a Swiss rock climbing venture capitalist who is very interested in seeing if there's any marketable, consumer market for this product. His dream is making a glove. Sometimes our thing is referred to as a glove. It's more of a paddle, that I'm kind of holding on to. He's really imagining more like a glove that would have the adhesives on the fingers, and not so much for climbing straight up a glass wall, but he's imagining, you're for rock climbing, where you try to, without the gloves, you keep getting stuck at this one spot, you keep slipping, you just can't quite make it across. And now he's imagining you put these gloves on, and then you have that extra, maybe it's only an extra 50% or something, but just gives you an extra bit that you can now hold on and not slip, and now you can go climb the rest of it, and go places you've never been able to climb before.
Oh, yeah, I can see that. That can be very appealing to climbing enthusiasts. And I imagine that you can probably, by structuring the ridges differently, make them a little more tolerant of a little bit rougher surfaces if you perhaps make them a little longer ridges, wedges.
Yeah, absolutely. And that's one of the reasons we've gone to this manufacturing process with the CNC machine. It's very easy to program a CNC. You basically draw it on the computer in a program like SolidWorks, a CAD program, and then you send it to the CNC, and it makes the shape exactly as you tell it. And so we're able to prototype and try new shapes, like definitely taller is one we're definitely looking at, depending on the surface.
Wow, well, that's absolutely super. This looks like there's a lot of interesting ways to go, places to take this. I think it's pretty clear you've done some amazing work. I'm sure you've got collaborators who have been of tremendous help to you, and doubtless a good advisor, and all those sorts of people. But I expect you must be getting and looking forward to wrapping up your doctorate and going off and taking this project into one or more of those interesting directions.
Absolutely, absolutely.
Well, I thank you so much for talking with me today, Elliot. It's been a real pleasure meeting you, hearing about this amazing piece of work you've done, and I wish you, of course, the very, very best with it. I'll be keeping my eyes out, and doubtless we'll be seeing about some of the wonderful applications that it gets put to.
All right.
Thank you again, and aloha to you.
All right. Thank you.
Yes, indeed. We've been with Elliot Hawkes of Standford University. I'm your host, Ethan Allen, here on Likeable Science on ThinkTech Hawaii, and signing off for another week of Likeable Science. We'll see you next week.